Freaky Physics again. Let me go to another screen, and I just need to set that real quick. There we go. Hello and welcome. Good evening, or good morning, or good day, good afternoon, good evening, or good night, wherever you are in the world, and welcome again to another stream. I keep saying that today. I'm still waiting for our student here. We have Gita today. And well, this was an not really emergency, but for those who were here yesterday, we kind of like talked about what we would be doing today. We're gonna continue with special relativity. So we're setting that up right now. All right, and here we go. Hello, Gita. Good evening. Well, good evening here.
Yeah,
Good
I
afternoon
really
over there.
appreciate that you're doing the lesson now.
No, don't worry about it. Okay, so excuse me. All right, so what are we doing? We're continuing the special relativity stuff, right?
Yes.
Okay. Okay, I think I may have found something a bit easier for us to go through. All right, so you sent over a few things. So let's see what those are first.
Yeah,
Okay.
I guess.
Uh-huh. Sorry, you're somebody's cutting off. Is it me or you?
Uh, I don't know. I hear a bit of a glitching, but
Yeah. All right, I think it's okay now. Uh okay. Um so this is the thing I want to share right now, okay? All right. And hey, Sebastian's on the stream. Hi, Sebastian. All right. So, let me. Where's the thing I was looking at? Hold on. Uh, Not that. Oh, here. All right. All right. Let's adjust that for now. Oh, I won't display. All right. I'll just display it on your board. Okay. For where is the Desmos? Okay. All right. Can you see that?
yes.
Okay. Um. All right, and we'll put it on the stream as well, just to see that. Okay. Um. There we go. Okay. Now, what I have here is basically let's remove let's move everything for now, uh, except these lines. All right. Now, what are these lines? Basically, what I have here. Yep. I'll just take away everything. What I have here is what you would normally see for a space-time diagram, depending on the reference frame you're talking about, right? So what I'll do is I'm going to take this line right here, okay? Now this, now you see that's not even a line. This looks like a no, not a parabola, but a hyperbola, right? Okay. Now this line here is going to represent what's called the space-time interval. Okay. Now, the space-time interval here basically is something that would be invariant between the two reference frames. There are gonna be four things that are invariant for the reference frames. Okay. First was the speed of light. It will be constant for both reference frames. The second one is the proper time. In other words, it's the time according to the one who's measuring it, right? Okay, the proper length as well will be invariant. And finally, we have the space-time interval, which is also an invariant. In other words, it doesn't change. Okay. For the space-time, we'll get to that later briefly, what that means. But I'm gonna also take a screenshot of this. Okay. Now I'm also gonna put in here one more equation here, y equals 0. Okay. Now that y equals 0, sorry, not y equals 0, should be x equals 0. Okay. All right, so this x equals 0 equation You see that here, right? That's
Yeah.
going to represent the stationary reference frame. Okay. Now, the next thing I'm gonna do is this. No, not that. Which one is good? Nope. Uh, I did one already. I think it's no, not that. It's this. It's this one. Okay. So let's say that this other line here is going to be our moving reference frame. So this we are S, and the other one here is the S prime, right?
Yeah.
Okay. You will see here that in this graph, this parabola intersects both these 2 points, 0.6 and 3.6 something 7, right? Okay. This means that for us in the okay, let's now say that there's an event, and I'm going to put that I'm going to this is our event right here. Okay, this is our event. Okay, now
Yeah.
let's say that also that our stopwatches start at the same time. So so when we are at this position where basically we're beside each other, both of our stopwatches measure 0. Okay, now this means that for the what's this for the moving reference frame S0, it takes 7 seconds between when we started and when this event happens. It takes 7 seconds. Okay? But
Yeah.
for us, it takes 6 seconds. All right? So that's one possible interpretation of that. So that's why basically we have okay, there. Okay? Now, what's the other possible interpretation here? The other possible interpretation here is uh okay, according to this, the two events. Okay, so the two events here, this start and this here, take 7 seconds, and it travels this much. So S0 would travel by this much to get to this event. Kind of okay. Now, here though, go ahead. I think you have a question.
Right. So if we are the straight line, the curved line is who?
Yes. So
What is the curved line represent?
this curved line, okay, so we'll get to that now. So you before we go there, you kind of get what it means in terms of the time, right?
Yeah.
Okay, so let's put this on the board now so it's easier for me to write on it. Okay, and we're using the same board as last time, as yesterday, so let's just open that. Apparently I haven't opened it yet. Okay, all right, that also means I'm moving over to this. Okay, didn't register. Let's do that again real quick. Okay, there we go. All right, so let's do this here now. All right, great. Let's put that image here. Well, okay, I see what respect. Well, we'll get to that as somebody has asked on the stream. What if it's wrong? Well, we'll get to that answer later. All right, excuse me. All right, so let's go back here. Okay, so again, I'm gonna use a different color now to make it easier to see. All right, so this is our space-time interval. Okay, interval. Okay, now what else
Yeah.
do we know here? Okay, we know that for S prime, 7 seconds pass from start to end, right? Let's just say from start to end to make it easier to imagine. Okay, What else do we know here? We know that the space we know that according to this, we know that it traveled um well, let's remove the unit. Let's not just say seconds here for now. Okay? Because that would be a bit wrong. But let's just say 7 units. Okay? 7 units of time. Uh 7 time units. Okay? And then also that approximately 3.6 space units pass by units were traversed. Okay, so that's gonna be a bit easier for us to kind of imagine. Okay, now in this case our space-time interval, we'll call that delta s, so this is gonna be our delta t or c delta t. Okay, we'll call that prime because it's in the prime, it's in s prime, right? So similarly, this is going to be our delta x prime. Okay, now it kind of looks like Pythagorean theorem because you kind of see a triangle, but at the same time it's not exactly a right triangle, right?
Yeah.
What shape do you see here? I think I mentioned that earlier. The shape we see here is a hyperbola, right? And
Mhm.
it so happens that for a hyperbola, the equation here will actually fit this equation. Delta s squared will be equal to c delta t prime squared minus delta x squared. Okay? Okay.
Like the equation of the line.
Yeah, so that's gonna be basically the equation of that line over there. Okay?
Yeah.
All right. Of that curve to be more specific. So this is its equation. Okay? Now, of course, this particular curve depends on what time you're using. So if, for example, if we go back here to the graph, we used 6 seconds as our time here, right? If we used
Mhm.
if we use t equals 5 seconds here, we're gonna use a different curve.
Yeah.
Okay. But anyway, we don't really need to know what the curves actually look like. We just need to actually know that we have this equation here for the uh what's this? For the reference frames and for the space-time yeah, the space-time interval. Okay. Uh
Yeah. And
go ahead.
sorry, after the t, what are the numbers?
Okay.
I can't really see.
Sorry, this is prime and this is squared.
Yeah.
Okay.
Okay.
All right.
Thank you.
So let me just redo that. Squared. Okay. So that's gonna be the equation, and as we said, this is also gonna be equal to c delta t minus delta x. I forgot the prime here. There should be a prime here for on the top. Okay. This is gonna be the same because they are invariant. Okay.
Yeah.
Okay. Uh. Okay. Oops, I forgot the squared here and the squared here. All right. So there we go. So because of that fact, we can now use these two equations to actually find uh okay. So in this case, again, what's did I actually pick? Yeah, I actually picked this. Now, this would have a speed of let's calculate that. Okay. Now, this thing has a gradient or a slope of 7 over 3.6. Okay. So this basically means what does that mean for us? We can find the speed. The speed is going to be equal to 7 divided by it's the other way around. 3.0 3.60555 divided by 7. That's gonna be 50% the speed of light, or 51.5. 51.5 c. That's the speed here, equals v. Okay. Uh, how we get that is basically you just do the slope thing we did yesterday. Okay.
Yeah.
All right. So once we find the speed, we can actually kind of calculate how far it traveled, because its time is 7 seconds, right? So the x here, or the delta x here, will be equal to uh that's going to be 51.5, a 0 point, sorry, that should be 0.515. Okay,
Hmm.
515c times how much time did it take? 7 seconds. Okay, so that's going to give us our delta x prime. So that's basically our delta x prime will be equal to what's this? That will be, let's just put that in the calculator. That's going to be 3.6. That's why we have this thing now. 3.6055. Okay? Okay. So this is gonna be, so this is our delta x basically, and this is our prime and delta t prime. See delta t prime here. Okay? Now, what are we gonna do now? Now that we know these, and we know that time for the stationary observer, we can now find the distance as measured by the stationary observer. Okay, so what we'll do here now is delta s squared is equal to c delta t c squared. I forgot the squared here again. Delta t squared minus delta x squared, and that should be equal to the prime versions. So c squared delta t prime squared minus delta x prime squared, right? So all we have to do now is put our values in. Uh, we know this is gonna be 6 seconds. So c squared times 6 squared. Okay. So minus our delta x here, we don't know. Then we're gonna put here c squared. Our delta t is gonna be 7 seconds. So 7 squared. Okay. So minus our delta x was the 3.6055 squared. All right. Then from here, it's pretty straightforward how to find our delta x. Okay, so from here we do finally delta x will be equal to, I'll just do the shortcut, uh c squared times uh 6 squared minus 7 squared plus 3.6055 squared. Okay, all right.
Yep.
So does that have a solution? Let's just put that in. That's gonna be 6 squared is 36 minus 49. It's gonna be minus 13c squared. Okay, plus this 3.6055 squared. All right, now from here we just calculate later on what this actual value is. It really depends on what our units are in here. All right, but that's the idea there. Okay.
Okay. And these are the Galilean transformations.
No, this is already special relativity. Galilean. Okay, if we go back to the graph, Galilean transformation would basically be this. Oops, let's hold on, let me just put something in. Y equals 6. All right, let me go back. I'll just copy this graph now again. So this, oh sorry, let's not put that thing up here. Right, this is what Galilean transformations would look like. Okay, hold on, I'm still gonna paste that. All right, basically for Galilean transformations, this is what happens. We have the same times.
Yeah.
Okay, so this is Galilean. Time does times are invariant. Okay. In other words, it doesn't change for time doesn't change for Galilean transformations. And with that, because of that, also lengths do not change. Okay. Also, okay. So basically, that's basically it. All right. Okay. Now there is another way for us to do the lengths, but I guess we'll just go straight to the problems you sent over. All right.
Okay.
Okay. Okay, let's see now. You want to do the new ones first or the previous ones?
I think previous.
All right, previous ones. Let's open them. Okay, there we go. Oh, we've done those two. All right. Which one looks good? Okay, let's do this. All right. Okay, so we have this problem first. So we have two relay trucks are on level horizontal tracks parallel to each other like this. There is an observer on each truck. Linda's truck is stationary and relative to the tracks, and Miran's is moving at a constant speed v relative to the tracks. Okay. Basically this is how they move. So
Yeah.
remember,
Okay. The first question.
okay, so let's go to the first question. Explain. Oh, we can skip the first question, right?
Yeah.
All right,
Yes.
let's take a look at next one. So we have Linda consider. So while this is pasting, let's read the problem. So Linda considers herself to be the origin of her frame of reference. Chooses her x-axis to be parallel to the tracks. Uh, okay, basically saying they both are their own centers of their reference frames, and they're both moving, and both our x's are parallel to the tracks. Okay. Now let's take a look here. It says there's a table at rest with respect to Myron's frame of reference. So in other words, the table is moving with Myron, right?
Yeah.
Okay. There's a clock on each truck which is at rest relative to the truck. Myron measures. Okay. The end of the table to be x prime and the other end to be at x2. As measured by Linda at time 2, the trucks are directly opposite each other, and at time equals t, they have moved x1 and x2. Okay. Using Galilean transformations only to deduce that both Linda and Myron will measure the length of the table to be the same. Okay. So the idea okay, so if we go to Galilean, how will this work? The transformation is this. In Galilean, okay, x prime will be equal to x plus vt, okay, and t prime equals t. Okay, so again, that's for Galilean transformations. Okay, so at this point, what is gonna happen? So if we go now into the actual problem, let's start with Myron. Okay, Myron. Okay. Um, Myron here measures. So what's gonna be the length of the table? That's gonna be x2 prime minus x1 prime, right? This is according
Mm.
to from Myron, right? Myron's reference frame. Okay, now we're gonna use a transformation here. Okay, and that's gonna be equal to what's gonna be x2. That's going to be x2 plus vt, right?
Yep.
Okay, and then minus x1 plus vt. What happens to the vt's?
Cancel.
They cancel out. We're left with x2 minus uh let's put an L bar here, L prime here, because this is from Myron's, right? So that's gonna be x2 minus x1 here, and because this is now unprimed, we now say that's the length according to Linda. So what do we see here? From here we get that L prime equals L.
Okay.
All right, so again, that's how we do Galilean. This is where you start.
And how do we know if we should use the Lorentz or the Galilean?
Generally speaking, if we're dealing with normal speeds like the ones we're used to, we just use Galilean.
Okay.
When we're dealing with speeds close to the speed of light, like at least around 10% the speed of light already, we can start using relativistic, or yeah, relativistic formulas. Okay.
So we said that time dilation and length dilation only happens in Lorentz.
Yeah.
When
So basically, yes. Lorentz. So time dilation. Dilation and length contraction. This will happen only in special relativity due to the Lorentz factor. Okay, let me
but
go ahead.
sorry. But why do we have then so many variables here, and they have different, like, um we still have the reference points and they have different, like, things that they see.
Um. Oh,
If
do you mean in special relativity?
in Galilean, like, depending on where the person is standing, they see it differently. Isn't that the dilation?
No, no, no. In the only thing that would be different in Galilean, generally speaking, is the positions. But so it's position, it's not length. You see the difference there?
Yeah.
Okay. So in Galilean, positions can change, but lengths don't.
Okay.
Okay, because remember, this x here, this is our position. It's better said that x is a position rather than a length. Okay, so the length
Mhm.
would be the difference in the positions.
Okay.
All right. All right. What else? So again, quick one before I forget. Remember that we usually call gamma as the Lorentz factor.
Uh, yeah.
Okay. Um, Actually, the only reason why it's called the Lorentz factor is actually Lorentz came up with it first. It just so happened that when Einstein tried to derive the equations for relativity, he got the Lorentz factor. So he didn't forget about it, so he called it the Lorentz factor as well.
Oh.
Okay, right. So anyway, that's just a bit of a story there. Let's go to the next question. Where is it? Okay. So Galilean transformation done. I think that's still Galilean. This is still Galilean. Actually, no. This one's done. What else? This one's done. Okay. We'll skip that for now. An observer in inertial reference frame S. Okay. Not. It's not it. Hmm. Okay. Let's take a look at this problem. This is actually a real problem that was. This is a real experiment that was done, and it's a really common example of how relativity works. Okay. Let's
Mhm.
go to the mu1 problem. Okay. Now, let me also get an image for that, just to I'll make it easier to understand what's happening. Okay. The experiment goes like this: mu1 relativity experiment. Okay, I'm looking for an image first, one that looks pretty good. Okay. Here. I'll simplify it for now. I'll just get the simplest possible one. All right. So basically, the experiment actually went like this. Okay, let's take a look at this idea here. Now, muons are basically, if you recall that from quantum mechanics, I don't think you actually studied that yet, but muons are basically heavy electrons. Okay, they're electrons
Right.
that have the 207 times the mass of a normal electron. Okay, now because they're so massive, they're radioactive. They decay rather quickly. So they have a half-life of that much. According to the diagram, it's 1.6 times 10 to the minus 6 seconds, but we'll use the value in the problem of 2.2. Okay, we'll use this value. We will ignore this value here. Okay, all right. Now, um, let's take a look at this now from what does it say here? If they're at rest, that's the half-life. So we know, so we're gonna look at this from the inertial reference frame of the mu1. Okay,
But what does it matter their address?
because when it becomes at rest, then this means this is the proper time.
Right.
Okay, because of the word at rest. Okay, so we're gonna say that S is for the mu1. Okay, for S, the delta T in this case is going to be 2.2 times 10 to the minus 6 seconds. Okay. Uh, okay. We don't know it's delta X, right? We don't know yet. Well, we
Yeah.
actually we do. Uh, okay, calculate the distance traveled by mu1 equal to the average that. Uh, okay. Three height of 3 kilometers above the Earth's surface. So, um, 3 kilometers. Okay, we don't know it's delta X. Okay, because that 3 kilometers is not the delta X. That's a delta X prime. Okay, why? Because that 3 kilometers is measured relative to us, the observer, the other observer. So we now are the S prime. Okay, so we don't know our delta T prime here as well, right? Okay, now we can do this one of two ways. The easier way to do this is to find our T prime. How do we find our T prime here? So,
We use the Lorentz.
yes, exactly. We use the Lorentz transformation. T prime should be equal to T times, I always have to think about it until I get to memorize it. Something gamma. Gamma is V over C, V over C small. So, small fraction will they flip over, multiply, okay? Because time will get longer, okay? So, this is gonna be the formula. What do we know? We know that the V in both of these cases, the velocity is 0.98 c. Okay, all right. So let's just put that value in here now. Our T is 2.2 times 10 to the minus 6 seconds. Our gamma is 1 over square root of 1 minus 0.98 c squared over c squared. Now the c again just cancels out. Now let's put that in the calculator. What's 0.98 squared? So it should be a bit smaller. 10. Okay, so this is gonna give us 2.2 times 10 to the minus 6 seconds times 1 over 0.0396. Is it?
Mm,
Square root. Forgot the square root. Okay. Let's take the square root of that now, and let's flip that over. That's gonna give us how much? It's gonna be 2.2 times 10 to the minus 6 seconds times 5.025. So we just do that now. We just multiply that by 2.2. 2.2 times the answer times 2.2. Okay, so that gives us 11.055 times 10 to the minus 6 seconds, or 1.106 times 10 to the minus 5 seconds. Okay. All right. So
yeah.
now that we've found our t prime, we can now do what? We can our
Mm,
t prime is again 1.106 times 10 to the minus 5 seconds. Okay? We've solved it. Now, what's the next thing we can do? We can actually do one of two things. Either we transform this x prime into x, right? Or we use the space-time interval. Both should give us the same results, so we need to check out if they both give us the same result. Okay. So, all right. So let's take a look here. What is gonna be t prime here? T prime will be, sorry, not t, delta x. Yeah. So
yeah.
delta x prime should be equal to delta x over gamma. Okay. So with that, so that's this is again solution one. Okay. Now what's this gonna be? This is gonna be 3 kilometers over. We'll use the 3 kilometers in the problem, so we'll change that there. Okay. Again, we already know what our gamma is. Our gamma is 5.025, right? So we'll just put it here over 5.025, and that's gonna be our delta x prime. And what's that gonna be? Uh, 3 divided by 5.025 gives us 0.5, well, 60 kilometers. Okay, so that's the one
Yeah.
possible solution. The other possible solution is using the space-time interval. Let's see if we get the same answer. Solution 2, space-time interval, right? Interval. So again, we're just gonna do straight away delta c delta t prime minus delta x prime should be equal to c delta t minus delta x, right? We know we have our values of c of our delta t already. So let's just put c here. Our delta t prime was uh 1.106 times 10 to the minus 5. 1.106 times 10 to the minus 5. And then our delta x is, we don't know that, delta x prime. And that should be equal to c times our initial time, which was 2.2 times 10 to the minus 6. Then the last one, minus delta x. minus 3. Let's put that in meters now, right? Okay. Now, let's see if we get 600. It looks like we're gonna get 600, right? So,
Yeah.
all right. But how are we gonna get here? Delta x primes. Oops, sorry. I forgot the squares. I keep forgetting to write the squares. So for me, if I keep forgetting to write the squares, you should also be careful by with this, okay? Square
On
here,
writing. Yeah.
square here, square here, okay? So what's gonna be our delta x prime squared? That's going to be c squared times this minus this. 1.106 times 10 to the minus 5 minus 2.2 times 10 to the minus 6. Okay. Then this goes to the other side as well, so that becomes plus 3000 squared. Okay. All right. So let's just do the math now on the calculator. That's gonna be 1.06 minus 2.2. It's gonna be, oh, I forgot to square them again, didn't I? Yeah, squared. All right, that's squared. Okay. 11.06 times 11.06 minus 11.06 squared minus 2.2 squared times 10 to the 6. That's gonna be 10 to the 12. So times 1 exponent negative 12. Then multiply that by 9 exponent 16. C squared is 9 times raised to 16. Then we subtract, or rather we add 3000, square that. Okay, so our delta x squared will get this value, 19,573, 19,573,524. So what's delta x? We take the square root of that. Let's see if we get the same answer.
Mhm.
We do not quite get the same answer.
Oh no. Yeah.
we get four. We get 4,424
Or
meters. Okay, which is higher? Let's see. Where did we go wrong here? Okay, just so you know, this is the correct answer. It should travel a shorter distance. Okay.
okay. Yeah.
All right. Okay. We'll see why we went wrong here in solution two. Let's see. I want to see why where we went wrong here. Okay. Okay. But anyway, so in this problem, it's gonna be easier to use the solution one of using the Lorentz transformation twice. Okay.
Hmm.
All right. So that's done. Any questions on the at least on the first method? Is that clear?
Yes.
All right. Uh, let's do that. Nuance search. Oh, this one's done. This one's also okay. There's a second part to this. Calculate the average lifetime of a muon as measured by the observer on the Earth. We actually just calculated that. Okay. So
Yeah.
as measured from the Earth, it actually is longer. Okay. The half-life becomes longer. So what does that mean? So remember, both of us see it correctly. The muons see themselves correctly, but we see it correctly. We just don't agree on what the actual answer is. It depends on what the basically depends on what's this? It basically depends on who's saying what. Okay. We've done this one.
Mm.
Uh,
But
let's try. on that.
Sorry.
Go ahead.
When we see the time it takes longer and like usually wouldn't reach 3 kilometers in its time,
Mm-hmm.
um, does it have something to do with the light traveling to our eyes, or is it solely the time
It's not
dilation?
even the uh okay, that's a good question, but I would have to say it's really just about the time dilation. The reason being that light has to travel at a constant speed no matter who's observing it, right?
Yeah.
Okay. Uh what's the your question actually has something to do with something else in relativity called simultaneity. Whether two events happen at the same time or not.
Right.
Okay. So do we have to do simultaneity here? Let me see the. Well, not in the problems. We don't have to do simultaneity yet. But I just want to see. Yeah, I think we have to go through that sometime. Simultaneity. Okay.
Right.
All right. Excuse me. So what else do we need? Can we do here? I think we can do one more problem here.
Yeah, there's one more continuation.
Uh, the continuation was actually to calculate the average lifetime, right?
Oh,
Which
yeah,
is what
I
we
guess took a picture.
yeah, we actually calculated that already. So I'll just put that little
Yeah.
bit there. Yeah, just put this little bit right here. Okay, so that's done. Distance is done. Okay, space-time diagrams. Let's just do that quick, I guess. So let's make this a bit smaller. Put it here. There. Okay. All right. An observer in an initial reference frame is at the exact center of train. Same time, lights are gendered turned on. Okay, this is gonna be easy, but I think there's a continuation to this problem. Okay.
Yeah, possible. I don't know if I
Uh,
took.
okay, let's go to this one. Okay, so okay, so the train car. So what? So because this is S, this is the stationary one, right? So how will the word line of the lights look like? It already says the lights, so you should know what the word line looks like straight away. If
Yeah,
this is CT, this is X, what should it look like?
like x equals y
X equals
line.
Y, like that. Okay. But don't forget the other side also, you have to draw that. Okay.
Yeah.
So this is just to keep it safe, just say that's 45 degrees. Okay. Also this 45 degrees. All right. There's no follow-up question right now, but I think there should be one. I think it has to ask about another observer from another inertial reference frame.
There should be. I'm looking at the picture right now, and it's a graph.
Oh, it's a graph. Or that's a continuation. All right then. Oh, because that's C, right? There's no part B to it though, so we'll skip B, I guess, for now.
Oh,
Okay. So,
I
uh,
messed it up.
all right. No,
Sorry.
don't worry, don't worry. Do you have it though? Part B.
I can find it.
Okay. Let's lock that for now. All right. Let's just do this problem for now. Consider those 2 points A, B, and C in Minkowski spacetime marked in meter units. So this is gonna be where B is. If we define the distance D between 2 points to be, find the distances between the points. Okay. If we define the distance D between 2 points in Minkowski space-time to be the space-time intervals square root, find the distances between the points. There is something missing. I think we need B for us to solve this. All right.
Yeah, I have
Have
it.
you said it yet?
But yeah, but I guess it's a bit overtime.
Oh, let me see first. I'm fine with it.
Okay, then we can finish this one
Yeah.
if you're
Okay.
okay with it.
Let's take a look at what this is now. Copy. So open that here. Copy that. All right. So let's put this in first for B. So we'll go to C later. Um, I guess we do B and then we can end here. And then for C, we can kind of do that fast. Okay. All right. So
Okay.
label each point wherein it's space-like, null-separated, and time-like. Okay. The easiest way for you to remember this is for time-like. Okay. Time-like separated means they are within the light cone. Now, you've heard. Do you know what the light cone means though? Before we move on.
No.
Okay. Okay. Let's go back to this. Okay. The light cone, we can actually extend these lines to here, right? Okay.
Mhm.
Now the light cone is this part I'm going to highlight. Okay. This is the light cone. Also, actually, this. It's called the light cone because that's how the light kind of sets a limit on the space-time diagram. Anything happening within the light cone means it's moving slower than light. Okay? And anything happening outside of that light cone means it's traveling faster than light. So this is let's just do one more label. This is the future light cone. Future light cone. This is the past light cone. Okay?
And what about like after the first light cone, the 45 degrees?
So this bit, right?
Yeah.
Okay. Okay. That's where we will have to explain this. Anything happening within the light cones, this is time like. So let me get that
Time
bigger.
like?
Yeah. These would be time like. Meaning
Yeah.
they may be separated by space, but you can link them by time. Okay? So time like
And they're
separated.
fast.
Yeah. So same
Sorry.
thing here. This is also time like. Okay? Now, here this is space like. Also here, this is space like. Okay. And then finally, go with the last part null separated. Uh okay. That's null separated. These lines that were v equals c, these are null separated. Or you can some sources call this like. Okay. So
What does it mean?
like. All right. I think it's for like it's a bit obvious when we say like rather than null. Light means it's traveling at the speed of light. So two events happening there, uh two events happening on the v equals c line or lines basically mean uh they can somehow interact only if they're both traveling at the speed of light. Okay.
Okay.
All right. Now, and because everything that we know of travels slower than light, then they can only interact in the light cone here, and that's why we call it time-like, because eventually they will interact after some time. Okay.
Yeah.
Now, so those two are obvious on the naming now. So I think it's gonna be easier to remember what time-like means and what light-like means, or null. Okay, space-like separation. Space-like separation. Basically, the idea here is they're so far apart that light cannot interact with that light from one. Okay, from one cannot interact with the other. And because the fastest thing in the universe is light, those two things cannot interact. Okay,
Mhm.
excuse me. All right, so interact with the other.
And so for time, like it's two things that exist but interact with time.
Yes. So okay, so let's go back to the problem now for C, just to kind of go through what it means. Okay. So label. Okay. So before that, which 2 points here are separated by are null separated? I think which 2 points are null separated. Basically, you don't look at the actual light cone. You look at whether the slope of that line is within the light cone or not. So basically, what you can do is you can make a new light cone from B, or you can make a new light cone from A, or you can make a new light cone from C. Okay, so that's the trick here. So I'm gonna do the 3 light cones like this, and see which two points are within the light cones of the other point. So let's take a look at A. A is not really a good point to pick, right?
Yeah.
All right. How about C? Are they? Well, let's take a look at B first. B is a good point to start with, because you can see that in B, your other 2 points are sort of on the light cone, right? Of B, in B's light cone. So,
Uh,
okay, so again, let's focus on making the light cone for B first. I will erase the rest.
I thought that null separated is the stuff on the light line.
Yeah. So exactly. So but remember that light cone or that light line doesn't have it kind of starts depending on who the observer is. So here, I just want to go back here then. This means this point here is um according to us. Okay? Us, which is the S reference frame, right? But we're looking here now is according to B. According to B. Okay? So since we're looking at things according to B's reference frame, we have to construct the light cones from where B is. Okay?
Yeah.
All right. So let's take a look at where B is. What's happening here? Which one is? I think it's pretty obvious. Which one is space like now? If we draw this light cone from B, space as rather, which one? BA, is that space like, null separated, or time like?
It's time like
It's time
A.
like. Okay, so this is A B. Okay. How about BC?
It's the null
Null
separated.
separated. Why is that the case? Because B and C are on the same light is in the same V equals C line for B, right? So this is null separated BC. So this leaves us a C for space like, right? Okay.
Yeah.
Now, this is what we mean now by space like. You see here, they're just separated by space. They're not separated in
Oh,
time yet. They're happening at the same time in this case, but they're separated in space, so they're not interacting yet.
but they're not in this section for space like.
Um, Actually, if you think about it, let's take a look now at a light cone. Okay, so and then I guess let's use green here. A light cone would look something like this, right? Where's C compared to a light cone? C is outside of the light cone.
Yeah.
Similarly, if we draw the light cone for C, A is outside of its light cone, right?
Yeah.
All right, so that's why A and C are space like separated. Okay, what does this mean
Okay.
though? Let's in this case, let's kind of put the trajectories up further like this, right? So C is gonna be here, and A is gonna be here. They're actually getting farther and farther apart in certain cases. That's a possibility, right? So in this case, they will always be space like separated, and they will never interact. A and C will never interact. But if A is going this way and C is going this way, like that, then they will interact at some time, at some point in time. Okay.
Right.
All right. Okay. We are really over time, so let's just do the last one here. If we define this, find the distance between the points. I guess. Okay, I guess we'll just do this on the next one. Okay.
Okay.
All right. So we'll end it here for today. All right. Do you have any
All right.
questions before we end?
No, it was really clear. I really like this topic now.
All right. Well, I tried to look for a good way to explain everything, but yeah, I think it's a lot clearer when you use space-time diagrams rather than you just use the plane equations.
Definitely. Yeah.
Okay. All right. So we'll end it here for today. Um, and I'll see you next time. Okay.
Yeah.
All right. Bye
Thank you
bye
so
now.
much.
You have a good day or good afternoon.
Have
Bye
a
bye
good
now.
evening.
Okay. Bye. All right. So that's the end, and let's go back to that question earlier from the beginning of the stream. What if special relativity was wrong? Uh, then it's a great thing for physicists. Because here's the idea. Special relativity is just an improvement. It's not a change for what we have always known. It's an improvement. So if special relativity is wrong, and then that simply means we just need to improve our theory, and we need to find a better theory that would better describe the world we live in or the universe we live in. So it's not gonna be wrong, totally wrong. It's still right in the cases that it works. A very good example here would be, hold on. A very good example here is, let's do it like this. Gravity. Newton's law of gravity still works. But modern day gravitational theory is actually uh, general relativity. In general relativity, is it better than Newton's law? It is. It is better. But is Newton's law incorrect? It's not incorrect. You still use it for cases that need to be simplified. Okay. The idea here is general relativity and Newton's law of gravitation. They actually say the exact same thing if masses are relatively small, distances are relatively small or large, and speeds are relatively small. Okay, so it really depends on the situation. So if we go back to that question, what if special relativity is wrong? Nothing. We just look. The first thing is we just look for a better theory, and the second part is it still works for certain cases, and in those certain cases, it may be easier to use the more simple versions. Okay, so with that, I hope that's the last bit there. I think the people on the stream are gone. Okay. Who's this? Hi, Mr. Dennis, whoever this is. I don't know who you are. I will find out because you know me. All right, but anyway, if you're still there, thank you for joining, and we will end today's or tonight's stream. Okay. Before we do though, don't forget to like, share, and subscribe to the channel. We're on YouTube, Facebook, TikTok, Instagram, and Twitch when we go live. All right, and again, I mentioned this earlier. I am on school breaks coming soon, and on the school break, I'm planning to work on this to make these processes a bit easier. So I just make one post and everything posts as well. Okay, so with that, I hope we can finish that before the school actually starts again, before school starts again. So, uh, watch out for the changes, especially for TikTok and Instagram. All right, so with that, everybody, I bid you all a good morning, good day, good afternoon, good evening, good night, wherever you are in the world. Take care, everybody. Bye bye now.